Good morning. We're all doing good. So I see how many? I see almost 7 people. So we may wait for 2 more minutes. And we'll start.
Good morning, sir.
Morning. How's it going, everybody? In the schools, online classes. How many chapters have they completed? Like first chapter, they definitely completed. Chemical reactions and equations. Acid, base, and salts, did they complete?
Almost completed, sir.
Almost completed. Okay. Now we will not be taking that much time as we took in the case of first chapter, because we spend a lot of time on like how to write the formula, like that itself went for 2 3 classes, right? So the ions, or the octet rule, all these stuff like the basics, right? So that took a lot of time. But acid base and salts will complete it very soon. Maybe in 2 3 classes itself will be completed. Okay. Okay, I think we'll start. We have almost 9, 10 people. Let me share my screen. Okay, fine. So today we'll be starting with acids, bases, and salts. Okay, so I would say we'll be starting with acids and bases. We'll study them together, or preferably we'll be studying acids first, then bases, then we'll go to salts. Okay, fine. Fine. So we have been we have been hearing this term acids, bases, salts, like say from our lower classes, say at least from the 6th class, you must have been hearing this. But we will be looking into what exactly the proper definitions, right? Say how do you define an acid? How do you define a base? What are the different types of salts? Right? Okay. And if I first after definition, we'll be seeing what to say, how are acids and bases classified, what are the different types of acids, different types of bases, right? And then we'll obviously look into the last part, we'll be looking into like how do we measure the strength of an acid, right? We know we have something called as some acids are very strong, some acids are very weak. First of all, what do you mean by strength of an acid, right? And how do you measure them, right? All these things you'll be studying, right? Okay. Now, what is the practical point of view? Obviously, you will be using acids and bases and salts throughout your life, in our day-to-day life, right? We'll be using. Like, let me tell you one thing, right? I don't know how you use it, but certain households use phenol for cleaning your toilets, right? So it's actually not phenol, right? It's actually phenol, right? Which is actually acidic in nature, right? So phenol, which it's actually not phenol, it's phenol. It eventually became phenol, right? So this is what we use in our, toilet for toilet cleaning purposes. And the structure is very simple. The structure will be like this, right? I don't know. You don't have to know the structures or not. I'm just telling you. This is benzene ring. It's a OH group. Anyways, so this is what phenol looks like. Okay, and basically this has some acidic properties, and that is why we're using it in your what to say, toilet cleaning purposes. Like that, you generally use acids itself, right? Generally, they use acids for cleaning purposes itself, right? And then bases we use, for example, say there's something called as milk of magnesia, right? So milk of magnesia is basically going to be an antacid, right? So when you have acidity, right? Say you didn't eat properly, you didn't eat on time, or say you had some bad food habits, something like that, right? So at that time, your acid content in your stomach will increase, right? The pH of your acid, or not, go to the pH and all. So your acid content in your stomach increases, and that gives you burps, that gives you kind of an irritation in your chest, right? So at that time, you take antacids, tablets, right? So these antacids are nothing but bases, basically, right? Obviously, if I want to neutralize the acid, right, I have to take some base so that it is going to neutralize the excess acid present in your stomach, right? And a lot of other bases we use, even the soap you use, are all basic in nature, right? The soaps you use are all basic in nature. All your bathing soaps, your cleaning soaps, whatever be the type of soaps you have, right? All of them are actually bases, right? And then say if you look at salts, we use a number of salts. Like one common thing is common salt, which we use in our daily in our food. We use sodium chloride, right? And then maybe we use for something called as rock salt. I don't know how many of you use it. Rock salt. Uh, it's not exactly kallupu, guys. Kallupu is different. Right? Anyways, so a lot of, and then say you go for baking powder, right? Baking powder, right? Baking powder is used for this thing, making cakes. That is also a salt. Baking soda. Baking soda is, again, it's actually not a salt. I would say it's a base, right? So, anyways, so you will see that this acid, bases, and salts are actually used in our day-to-day life very extensively, Okay, right? And then when you go like, and obviously these acid bases and salts are also used in chemical laboratories for preparation of some other chemicals, right? Especially if you go for organic chemistry. Organic chemistry is basically, the study of carbon and its compound. The last chapter you have in your 10th class, right? You will not be studying it now, but maybe when you go to your 11th class, right, you will be using these acids and bases for performing certain reactions, right? Even when you go to 12th class, so many times you'll be using these acids and bases, even sometimes salts for a lot of reactions. Okay, so these are all the purpose, these are all the real-time applications of these acids, bases, and salts. Right? Okay, so we'll move on. We'll move on to see what is the definition of acids and bases. Right? The first we'll see what is the definition of acids and bases. Salts we'll see later. Okay, but for now we'll look into what is the definition of acids and bases. Right. Okay, guys. There are going to be three definitions, but again, only one definition is there in your syllabus, right? Okay, but I'll give you all the three definitions, right? But again, only one of them is going to be there for your 10th class. But when you come to 11th class, you will be using the other two definitions also. Okay, fine. The first concept or the first definition comes from a scientist called as Arrhenius, right? So we have something called as Arrhenius concept of acids and bases, or so it's called Arrhenius theory of acids and bases, or Arrhenius concept, or it is also called as Arrhenius theory of acids and bases. Okay, so what this says, right? What this Arrhenius theory says is that you have a species, right? You have some chemical species with you. Okay, when can I call that particular species as an acid or a base? Is that you take the chemical species, right? You dissolve them in water, right? You dissolve them in water, and if after dissolving in water, if you see that H plus ions are produced, right, that is going to be termed as an acid. So very simply we can put, so I have some species, chemical species, right? You dissolve in water, right? And then if you find that in the water, in the solution, right, this is the solute, H2O is the solvent, so you together it forms the solution, right? So in the solution, if you find H plus ions, right, that particular chemical species which you're talking about, that chemical species is going to be termed as an acid. Okay, guys, you should not be telling I like anything which produces H plus is an acid. No, that's a very wrong statement. You should dissolve that particular thing in an acid, sorry, in water. And if it produces H plus, then only it is an acid. Okay, say like there's a very famous question I can ask you. Say I have HCl gas. Okay, I have HCl gas and I have HCl aqueous. Right? Now tell me, out of these two, right? Out of these two, which do you think will be an acid? From the definition which we saw. Gas or aqueous solution?
Aqueous solution.
Absolutely, right? Say, remember, this cannot produce H plus. Gas, HCl gas is existing, right? It is a compound, it is existing in gaseous space. Okay. Now that HCl gas cannot produce H plus as long as you dissolve this in water and then you form this HCl aqueous solution. This can form H plus. Yes, absolutely. Okay, right? So remember, only if you have these aqueous solutions mentioned, only then it can give me H plus. If they give you solid, liquid, gas, none of them will produce H plus. Right? Any of these things, solid, liquid, or gas, whatever it is, if you dissolve them in water, then it becomes an aqueous solution. Then you have to check for whether it is producing H plus or not. If it produces H plus, yes, wonderful, that's an acid. Okay, you have to be very careful in this. Right, fine. Same way, I'll be able to define what are bases, right? Same way, there should be some chemical species dissolved in water, and if it produces OH minus ions, right? OH minus ions, it's going to be called as base. It's called as basic in nature. Okay, so there's going to be some chemical species dissolved in water, right? See, this thing represents that ditto. Ditto means what? Whatever I wrote here, the same thing will come here. Okay, this one I think you should know. Anyways, so if it produces, if you dissolve and if you find that there are OH minus ions, Okay, now that chemical species, right? That chemical species is what is going to be called as a base. Okay, same way, like as I said here, only and only aqueous solutions, base, aqueous, only will produce OH minus. Okay, right? Fine. Now, guys, sometimes, right? What they will tell you is that this H plus ions we're talking about, right? Right? This H plus ions are very unstable. Right? These H plus ions are very unstable. That means what? Like if you try to find them in the solution, right? After mixing, after dissolving the chemical species in water, right? If you're trying to find H plus, right? Actually, you will not find, even though it's an acid, right? You will not find H plus directly. This H plus will be in some other form. Okay, now what form it will be? Very simple, right? See, please understand. If I write the reaction, for example, I have HCl. Okay, now HCl is going to be dissolved in water. HCl is going to be dissolved in water. I know this HCl is capable of giving me H plus. Okay, this HCl is capable of giving me H plus. Okay, now H plus comes from this, right? H plus comes from this, and it is going to be accepted by the water molecule. Remember this. Okay, H plus comes from this, and it is going to be accepted by the H2O molecule to form. Obviously, if I remove H plus from this, what is remaining? Only Cl minus is remaining, right? And after the what is remaining, H plus attacking H2O to form H3O plus. Very, very important. It's called hydronium ion. Okay, hydronium ion. Right. So I can go back to the definition, people. Say a species which produces H plus on dissolving in water is what is called as acid. Now, instead of H plus, you can even write H3O plus. And that's a correct statement. That is actually a better statement. Okay, why? Why it's a better statement? Because the HCl ions you see, right? Sorry, H plus ions you see are unstable. Right? Why they're unstable? It's very simple, right? Hydrogen had only one electron, atomic number 1. Now, if it is H plus, there are no electrons here. Right? Exclusively a positive charge. A proton alone is present. Right? If you look at the configuration, I had hydrogen to have one electron, one proton. Hydrogen. Right? Now, if this becomes H plus, what will happen? This electron is gone. Right? And only one proton is remaining. That's why we have a positive charge. Right? Only one proton is a positive is remaining. That's why it's unstable. Okay, right. So the correct way of telling it is it is going to produce H3O plus, that is hydronium ion, and that is only responsible for the acidic nature. Okay, so this is how you write the reaction. HCl, when it dissolved in H2O, you form not H plus. H plus is coming from this obviously, but that is not going to stay like this. It is going to be accepted by water molecule to form H3O plus, that is hydronium ion. Okay, this you have to remember. Sometimes they will tell in terms of H plus, sometimes they will tell in terms of H3O plus. Either way, right? It is going to be talking something about acidic nature of the substance. Okay, right. Fine. And this OH minus is not, there's no change in this. OH minus will exist OH minus only because it's not only a one electron, one proton. There are a lot of other stuff involving here in OH minus, right? And hope you all know OH minus ion is called as what? What is the name of OH minus? Like say H3O plus, I call it as hydronium. Like that, OH minus is called as what? What is the name of the ion? OH minus. Okay. Say for if at all you don't understand the question, say for example, when I say SO42 minus, what is the name of the ion? SO42 minus ion. What is the name of the ion? Hey, are you there?
Sulfate.
Okay. Hydroxide is correct. Hydroxide is for OH minus. Yeah, correct. Right. Hydroxide. Right. So the problem is we are meeting only weekly once. That's the problem. You are forgetting. Right. So anyways, this is called sulfate ion, and OH minus is called as hydroxide ion. Very simple, right? I have hydrogen, oxygen, OH minus. And obviously it's a negative charge, so it has to end with IDE, hydroxide. Right? Anyways, so we understood what.
Sir, can you explain once more why H plus ion is unstable, sir?
Yeah, sure. So what happens here is that I know hydrogen is contain atomic number of 1, right? Hydrogen has an atomic number of 1 electron, 1 proton. Right? Okay.
Yes,
now for me to produce H plus, what has to happen from hydrogen? This hydrogen has to lose this electron to form a positive charge. Correct?
Yes, sir.
So obviously, if this loses electron, only 1 proton is remaining, right? Only 1 proton is remaining, right? Excuse me. Okay, so instead of writing this H plus, I can just write it as a proton, right? Because already I had only 1 electron and 1 proton. That 1 electron is lost, right? So I produce only H plus, which contains only 1 proton. And obviously, if I have only 1 proton, it is going to be unstable. Only 1 small positive charge. That's why it is unstable. Okay. Or I can tell it this way. It is so unstable. Why? Because it is highly reactive. Right? This particular H plus is so very, very highly reactive that's why it's unstable. Remember, guys, reactivity and stability are inversely related. Right? So if something is very stable, that means obviously it is not going to react that much. Right? But if something is so much reactive, obviously it is going to be unstable. Right? Remember, stability and reactivity are inversely related to each other. This is high means that is less, and vice versa. Okay. Now, the moment H plus is formed, it is going to react with water molecule H2O to produce H3O. Okay. Is it okay, Gana? Understood? Homework asked. Okay. Fine. Yeah. Cool. So that's about what is the definition for acids and bases. Right? Anything produces H plus on dissolved in water or H3O plus, that's called acid. And if it produces OH minus on dissolved and non-dissolving in water, hydroxide ion, it is called basis. Right? That is what is called as my Arrhenius concept. Okay. Now, I told you that there are going to be 2 more theories. Right? There are going to be 3 theories totally. Right? Now we'll see the next one. Next one is what is called as Lowry-Bronsted theory, or Lowry-Bronsted concept, or however you want to call it. Okay, right. Now, why are we even going to this? Right? Why are we going to this theory? Right? It's because people, there are certain species. Okay, there are certain, for example, if I tell you that beryllium chloride, right? Beryllium chloride is an acid. Will you believe that? Will you believe this? No, because why? Because you know only one definition. If I dissolve this in water, can it produce H plus? Is the question. The answer is no, not exactly. Right? There are so many things like this: BF3, beryllium chloride, so many other things like this. Even aluminium chloride, right? All the aluminium oxide. Anyways, so the thing is, there are so many species like this, right? Which doesn't produce H plus, but still they are going to be called as acids. Right? If I dissolve them in water, they don't produce H plus, right? But still they're going to be called as acids. Okay. Same way, if I have something like ammonia, I know ammonia, right? Ammonia NH3. Ammonia is a base, right? But see, is it going to produce OH minus when it dissolves in water? Yeah, it does. But by looking at the compound, by looking at the formula of the compound, you don't see any OH minus ions. Right? So for these, to overcome all these problems, something doesn't give me H plus, but still is an acid. Something doesn't give me OH minus, but still is a base. So obviously that particular definition, what we saw here, that is Arrhenius concept, is not enough. Yeah, majority of the cases, yes, this is going to work, no doubt about it, right? But for some cases, right, this particular theory doesn't work. Okay, right. So what does Lowry-Bronsted theory says? Right? What does it say? It is going to talk in terms of protons. Okay, so the thing is, whichever is able to donate a proton, right? Whichever is able to donate a proton, it's called an acid. Lowry-Bronsted acid, it's called. Okay, whichever is able to donate a proton, right, is going to be called an acid, and whichever is able to accept a proton, that is going to be called as a base. Okay, whichever is able to donate a proton, acid, whichever is able to accept a proton, base. Right. I think, guys, this you will be able to easily understand. Why? Just now I told you that H plus is nothing but a proton. We already discussed this. Just now we discussed this. Hydrogen had one proton. I remove an electron to form H plus. So what is remaining is just a proton. So obviously anything which gives me H plus is an acid. That's what indirectly it says, donating a proton. Which, say for example, HCl will be able to donate H plus to some other species, right? So obviously HCl I'll call it as an acid. Okay, but this doesn't give me any, not so much difference there between this definition and the Arrhenius definition. But when I go to the base, that is accepting proton, it actually gives me some insight, right? What it gives me insight is, if you look at ammonia, for example, right? Ammonia, right? If ammonia is able to accept a proton, in the sense that, see, this is going to accept the H plus, right? This is going to accept the H plus to form NH4 plus. And can someone tell me what is the name of this ion? NH4 plus. What is the name of the ion? What is the name of this ion, guys?
Ammonium,
NH4 plus. Ammonium ion. Okay, so this is ammonia. Okay, so anyway, so what are we trying to establish here is that this NH3 is, like, say, if I dissolve it in water, I'll show you how it is going to form OH minus, but a little complicated. But what you have to understand is this NH3 can accept a proton, or say accept a proton means can accept a H plus to form NH4 plus, right? So obviously, according to this definition, it is able to accept a proton. So NH3 can be called as a base. That is a Lowry-Bronsted base. Okay, right? Fine, guys. Like, if at all you don't want, this is just a little out of the book, right? You don't have to remember this, but knowing extra information is always good. Say if you want to write your Olympiad exams. Any doubts? Anybody wants to ask me anything? Okay, fine. So that's what. So for the sake of a competitive exam, say Olympiads, or say like any other kind of exam which you want to write, all these things are very, very important, right? Lowry-Bronsted theory, Arrhenius series is one more which is going to come, right? All these are pretty important. Okay, but for your school level, only the first one, that is Arrhenius concept, is enough. Okay, right, fine. So we understood, right? What does Lowry-Bronsted theory says? Donating a proton is an acid. If something accepts a proton, whichever accepts a proton, that is a base. So basically NH3 is a base because it is able to accept a proton, that is H plus, to form NH4 plus, right? Okay, now the third and final theory, right, which is what is called as Lewis theory. Right? Is something called as Lewis theory. Okay, now see, in chemistry generally, right? So even though we have electrons and protons, positive charges, negative charges, and all that, right? We generally speak only in terms of electrons, right? Say now you might have even seen in case of how do you form a cation? We say that electron is removed, right? So for example, if I want to form Na producing Na plus, how do we say this? Obviously, sodium has to lose an electron. That's what we say. Why can I not say that Na accepts a proton to form Na plus? This is also correct, right? Is it not? See, Na producing Na plus by removing an electron. I remove a negative charge so that the remaining will become a positive charge. Why can I not add a positive charge so that it becomes Na plus again? It is all convention. Okay, it's not like this is not right. This can be right. Right? But by convention, we see only the electrons will move, right? Only electrons will move. Protons are stationary. Okay, electrons will move and protons are stationary. So this donating proton, accepting proton, right? So that means what? Proton should move, right? And that is not going to happen. It's not like it's not going to happen. it is tough for us to, see a proton moving. Okay, now tell me, any idea? Okay, right. There is something called as mobility. Mobility means ability to move. Okay, mobility means ability of the species to move. Okay, now what I'm telling is electrons' mobility is greater than protons' mobility. Can someone come up with an explanation for this? Electron can easily move when compared to a proton. Any explanation, any guesses? Why is it like this? Guys?
Electron is lighter than the proton.
Absolutely, absolutely, that is right. Right. So when I compare the mass, obviously, see, think about this. A smaller species, a species having lesser weight, can move faster. Right. We can take the example of running races. A person who's very lean will be able to run faster than a person who's little more, more sturdy than him. Right. Okay. So what I'm trying to say here is that the mass of electron is very, very, very less when compared to mass of a proton. Right. So obviously protons are very heavy, right? So they will find it difficult to move, but electrons are very small and they are very light in weight, so that their mobility is faster, or they move easier with respect to the movement of protons. Okay, so because of these reasons, right? So even though this gives us a better institute, like better insight, like in terms of an acids and bases, that is accepting proton, donating proton, but this doesn't give the full insight, because generally protons doesn't move. It is the electrons which moves. Okay, so Lewis theory obviously is going to be saying talking about acids and bases in terms of electron and not proton. Okay, so we'll see what it says. What does Lewis theory says? We'll see. So what it says is that if something is able to accept a lone pair of electron, it's called an acid. Same way, whichever is able to donate a lone pair of electrons are what are called as bases. Okay, fine. So we'll see what is this. Okay. Now guys, do you know what is a lone pair of electron? Anybody knows what is this? Lone pair? Okay, fine. That's a new term, right? Lone pair of electrons. Okay, guys, do you know Lewis dot structures from your 9th class? Lewis dot structures, like say we write like this. For example, for hydrogen, if for H2 molecule, this is how we write. Say hydrogen has 1 electron, this hydrogen has 1 electron, so I require, this hydrogen requires 1 more electron to satisfy its octet, so it will take this. This hydrogen requires 1 more electron to satisfy its octet, so it will take this. So I write H bond H. This you know? Do you know this kind of structures, Lewis structures?
Yes, sir.
No. How is it possible that you don't know? 9th you had this, right? Atomic structure or something, some chapter you should have this.
So we had the atomic structure, sir, but what you are saying we did not learn.
Oh, fine. Fine, don't worry about it, right? So if at all you don't understand this lone pair of electron, just forget that, just forget this lone pair. You don't have to even speak about this, because I have to spend some time for you to understand what is lone pair. So forget about lone pair, right? So if something is able to accept an electron, or I would say accept an electron, it's called an acid. Whichever is able to donate an electron is going to be called as a base. Okay, right? Fine. Now look at this. I will take some examples. Take barium chloride. This example I told you that this is an acid, right? But still, it is not going to give me H plus. Okay. Now how? We'll try to understand. Okay, fine. Now beryllium, people, has an atomic number of 4. Beryllium has an atomic number of 4. So now what will be the configuration? Configuration will be 2, 2. Okay, configuration would be 2, 2 will be the configuration. Right. Now please understand there are 2 chlorine atoms, right? 2 chlorine atoms are there, and each chlorine atom, right? 1 chlorine atom will give 1 electron. Okay, 1 chlorine atom will give 1 electron to beryllium. Okay, so if I have two chlorine atoms, 2 electrons will be given to beryllium. Right, 2 electrons will be given to beryllium. So what will happen if if 2 electrons are accepted by beryllium? Can I say the configuration will become 2,4 for beryllium? Okay, again I repeat, people. Beryllium has an atomic number of 4. That means the configuration is 2,2. Electronic configuration is 2,2. Okay, now chlorine here, I have 2 chlorine atoms. These two, each of the chlorine atom is going to donate 1 electron to beryllium. No problem. Okay, now since I have 2 chlorine atoms, totally 2 electrons are going to come from chlorine to beryllium. So what will happen to the configuration? 2, 2 was there. You add 2 more electrons, it is going to become 2, 4. Okay, 2, 4. Now, is this stable? Like when I have this configuration, is this stable? Or if it is not stable, why is it not stable? Why this 2, 4 is not stable? Is someone saying something? I'm not able to hear.
It
For me to
hasn't
have a
completed octet.
that's the point, right? It is not octet satisfied, right? I need to have 8 electrons here, right? In this place, wherever I have 4, I should have had 8 electrons. Only then it is stable. Or say this 4 electrons shouldn't have been there. Only 2 electrons should have been there, and then it would have been stable, right? So either way, what you understand is this configuration is unstable because octet is not satisfied. Right, so what happens now? I can, so that means for it to become stable, I can still accept 4 more electrons. Right, this beryllium chloride can accept still 4 more electrons because its octet is still not satisfied. Even though you form the compound, right? Even though you form the compound, you see octet is not fully satisfied for beryllium. For chlorine, it's okay. Chlorine will form. Right, for beryllium, it's a problem. So we cannot speak about beryllium separately here because still a compound. Beryllium chloride can still accept 4 more electrons because octet is not satisfied. Right, so I will call beryllium chloride as a Lewis acid. Why? Look at this definition. Whichever is able to accept electrons are what are called as acids. Right, now BeCl2, since the octet is not satisfied, it will be able to accept more and more number of electrons. Okay, and that is the reason why it is going to be called as an acid, Lewis acid. Okay, right. Same way, I can give you one more example. Look at this. When I have boron trifluoride, BF3. Okay, now boron has an atomic number of 5. That means the configuration is 2, 3. Right, now again, 1 fluorine atom will give 1 electron. Now I have 3 fluorine atoms, so it will give 3 electrons. So the configuration will become 2, 6 for boron. Still, octet is not satisfied, right? You can accept 2 more electrons, right? So still can accept electron. So again, I will call BF3 as a Lewis acid. Very simple. Okay, I'll call BF3 as a Lewis acid. Right? Fine. So again, hope you understand how is this. 5 is atomic number, 2, 3, 1 fluorine atom, 1 electron. So 3 fluorine atoms will give 3 electrons. So configuration will become 2, 6. That means still it is not octet satisfied. So obviously it can accept more electrons. So now this is going to be called as a Lewis acid. Okay, right? Fine. Maybe I'll give you an example for a Lewis base. Okay, say again, I'll take the example of ammonia. Right. Now, guys, I think I have to go for the Lewis dot structures for you to understand how is this. Right. See, understand, nitrogen has atomic number of 7. So it is going to have a configuration of 2, 5. Okay. And hydrogen, obviously, I know has only 1 electron. Atomic number of 1. Okay. So if I want to see how the bonding and all is formed, you should take only the valence electrons. Correct. So nitrogen has 5 valence electrons. Okay, these are the 5 electrons in the last shell, valence shell. Okay, and there are 3 hydrogens, and each hydrogen has 1 electron. Okay, each hydrogen has 1 electron. Okay, now for hydrogen, duplet need to be satisfied. That means I already have one electron. I just require one more electron for it to satisfy duplet. Right? It requires only one more electron to satisfy its duplet. So what will happen? This will take one electron. Again, this hydrogen will take this electron. This hydrogen will take this electron. Okay. Now for hydrogen, duplet is satisfied. Okay, hydrogen has become stable. Right. Now what about nitrogen? Nitrogen has 5 valence electrons. You can see 1, 2, 3, 4, 5. 5 electrons are there. Now for me to satisfy octet, I require 3 more electrons. Right. So obviously from each of the hydrogen, it is going to take one electron. So I am going to have all these 3 things taken. Right. You will see 1, 2, I mean 1, 2, 3, and already I had 5 electrons. Now nitrogen has 8 electrons. That's it. Okay. Now you see there are 2 types of electrons now in the valence shell for nitrogen. One which is involving in bonding. You can see this electron, and this electron. Hope you're able to see the marking again. Maybe 1, 2, and 3. These 3 electrons are mutually shared with hydrogen. These 3 hydrogens. Okay, but you look at this one, this particular pair. This particular pair is there in the valence shell, but it is not shared. Right? It is not shared with hydrogen. It is only there in nitrogen. It is only there in nitrogen. So these kind of species, like this kind of pair of electron which is there in the valence shell, but not shared in the covalent bond. Again, I repeat, these kind of electrons which are there in the valence shell, but not shared with other species to form a chemical bond are what are called as lone pairs. I think from the name, it's a pair of electron and it is alone because it is not shared. Right? These 3 electrons are shared. 1, 2, 3 electrons are shared with hydrogen. But these 2 electrons which are here are not shared with any other species. It is there only along with nitrogen. It's there in the valence shell. Okay. So these are what are called as lone pairs of electrons. Okay. Even H2O will have this. If at all you want me to explain how it is, it's very simple. Right? Oxygen has atomic number of 8. So it will have 2, 6 as the configuration. Okay. So same way hydrogen is having 1. So I'm going to have H2O. Okay. So oxygen in between. So oxygen has 6 valence electrons. Okay. So I write 1, 2, 3, 4, 5, 6. Okay. And hydrogen has 1 electron. Each hydrogen has 1 electron. So same way this hydrogen will take this electron to satisfy its duplet. This hydrogen will take this electron to satisfy its duplet. Again, oxygen has already 6 electrons in the valence shell. It requires 2 more electrons to satisfy its octet. Correct? Oxygen requires 2 more electrons to satisfy its octet. Now you'll see this electron and this electron will be taken. Now that's it. Octet is satisfied. Right? But you see, this particular pair and this particular pair are okay. Right? This particular electron of oxygen and this particular electron of oxygen are shared with the hydrogen. But what about these 4 electrons? These 4 electrons are there in the valence shell, but again they are not involving in bonding. That is, they're not shared with some other atoms. So I would say this case has 2 lone pairs. Right? Like say in H2O, oxygen has 2 lone pairs. In ammonia, nitrogen has 1 lone pair. Anyways, so the thing is, this lone pairs, what you see in ammonia, forget about water, right? So this lone pair, what you see in ammonia, we write like this: ammonia with 2 dots on top of nitrogen. This means that nitrogen has a lone pair. Okay. Now these 2 electrons can be donated to some other species. Okay, these 2 electrons can be donated to some other species. Okay, so obviously, if this can be donated, now look at the definition. Anything is able to donate an electron. I would say donate a lone pair of electrons. So now you can understand what is a lone pair. Donate a lone pair of electron. That is going to be called as a Lewis base. Okay, that is going to be called as a Lewis base. Okay, so ammonia is a Lewis base because it will be able to donate the lone pair to some other species. And whichever is able to accept a pair of electrons, those are what are called as Lewis acids. That is BeCl2, BF3. There are so many other examples, but you don't have to go into the details. Okay. Anybody has any questions? Anybody want to ask me anything in whatever we saw till now? Any questions? Okay, I suppose everything is clear. But again, guys, you don't have to remember this Lowry-Bronsted theory and Lewis theory for your school exams. Okay, this is just extra information for you. Okay, all we need is this. That's it. Arrhenius concept. That is, anything which gives me H plus or H3O plus when dissolved in water, that's an acid. And anything which gives me OH minus ions when dissolved in water, those are what are called as acid bases. Okay, right. Fine. So that's about the definitions. Now we'll move on. We'll move on to see what are the physical properties. Okay, we'll start with acids. Okay, now we'll not see acids and base together. We'll see them separately. So physical properties of acids. Okay, now this chapter is already taught in your school. At least this part would have taught. Can you tell me what are all the properties, guys? Come on. What are the physical properties of acids?
Sir, acids are sour in taste.
Acids are sour in taste. Okay, I think it's bases. Yeah. Okay, that is a very good point. They are corrosive in nature. Now you must have seen a lot of movies. Like I don't want to take that as an example. Anyways, so you must have seen that like even if a drop of acid falls on you, or the skin will start corroding, right? So that is very corrosive. Even when you go to your labs, you have to be very, very, very careful in handling acids. That too, a concentrated acid, you have to be very, very careful. Okay, fine. So they are corrosive. So someone said sour in taste, but not all acids. Okay, some of them, like obviously nobody can taste an acid and tell, okay, this is the taste. Right? That's a very unrealistic thing, right? Anyways, so it's corrosive. Okay, something is little sour, and obviously most of them are aqueous solutions. I mean, all of them are aqueous solutions only. Anything else you want to tell?
When solutions of acid turn blue litmus paper to red.
Correct. This also we can say, right? They turn blue litmus to red. Okay, we'll see this. We'll see about this in detail. Don't worry. Okay, this is just a physical property. We'll see about this in detail when I go for indicators. Okay, now that's a statement you can take down. Okay, so yeah, these are all the physical properties, and sometimes acids have a pungent smell. Okay, what do you mean by a pungent smell? Okay, some of you would have smelled turpentine. You know the turpentine? Okay, say if
Yes,
I want to. Okay, turpentine, if at all you don't understand. Petrol, okay, petrol obviously would have smelled, right? So not that kind of strong, like what to say, like something goes inside and tears comes out. Like that kind of smell is what is called as your pungent smell. Very strong, like it just hits you. Like that kind of smell is what is called as pungent smell. Okay, so these are all the different physical properties of acids. Okay, now this is not that important. Next thing, which you're going to see, is about the classification. What are the different types of acids we can have? Okay, classification. Okay, now there are going to be different ways in which I'll be able to classify. Right? Say the first one is based on source. Right? First one is is based on source. Okay, where do you attain these acids from? Right, based on that, I will be able to speak about this. Okay, so under this, I have two categories, right? One are what are called as organic acids, right? Another one are what are called as, I would say, inorganic, or it is also called as synthetic acids. Okay, from the name itself, we can another thing understand. Organic acids are obtained from nature exclusively, right? They're obtained from nature itself, right? And these inorganic or synthetic acids are, say, semi-nature, like say some derivatives are there in nature, or they are produced in labs. Okay, right. Fine. I mean, some of the organic acids obviously can be prepared in laboratories also, right? Say, for example, oxalic acid or something can be prepared in labs also. But again, the primary source is nature. Okay. Okay, fine. I think again you must have seen so many examples, guys, for organic acids, right? Now you must know what is the acid name of the acid, and what is its source. Yes, go on. First one. Anybody?
Citric acid.
Okay, citric acid from source.
Lemon.
Okay, any citrus fruit. Okay, any grapes, lemon, orange, all of them will contain citric acid. So citrus fruits, I call it. Okay, next.
Tartaric acid.
Okay, tartaric acid. Okay, the source. What is the source of tartaric acid?
So tamarind.
Tamarind, yes. Tamarind is puli, guys, in Tamil, like we use for keeping rasam and all, right? Okay. Anyways, next, third one. Then
So
citric
acetic
acid, acetic acid. Okay. Where do you find this?
So vinegar.
Okay. Now, vinegar, it's not a natural source. Okay. Anyways, okay, this acetic acid is also found in wasp bites. There is an insect called as a wasp. I don't know whether you have seen it. It in Tamil, it's not exactly vetiki. I don't know what exactly it's called in Tamil, guys. Wasp is like dragonfly, something like a dragonfly. Okay, so if it bites, okay, if it bites you, that bite contains acetic acid. Okay, that bite contains acetic acid. Okay, this also I can remember. Okay, next one.
Lactic acid.
Okay, good. Lactic acid. Where do you find this?
So milk.
Okay, milk. Okay, but actually the more primary source is curd. Okay, now I think we will be able to easily understand based on the taste, right? Curd will be little sour in taste. Milk is not sour in taste. Okay, so curd will contain more amount of lactic acid than milk. Okay, right? Because you can understand the taste itself, like it's little sour, right? Curd is little sour. Okay, anyways, next lactic acid. Okay, then
Oxalic acid.
okay, oxalic acid. Where do you find this? Where do you find, guys? 1 second. One
The
second.
tomato.
Background. Yeah, correct. 1 second. Hold on. Okay. Yeah. Yeah, malic acid. Yes, malic acid is there in apples. Okay, first we complete this. Okay, correct. Aditi, whatever you're telling is absolutely right. Okay, so oxalic acid is there in your apples. Anything else you know? Oxalic acid is present.
So pepper.
Sorry. What?
So pepper
Other
or
than
tea.
pepper. Pepper contains oxalic acid. I've never heard about it. Maybe I'll check about this. But I've never
There is
heard.
oxalic
Maybe.
acid present in apples.
Yeah, apples we wrote. Yes, oxalic acid in apples. Other than apples. Other than apples, oxalic acid is present in two more fruits or vegetables.
So tomato.
Yes, tomato is one. Tomato contains oxalic acid. There's one more. Contains oxalic
Spinach.
acid. No, not spinach. It's a fruit. Any guesses? Maybe in the chat box, anybody wants to tell? No? Okay. Fine. So the answer is grapes. Okay. So even grapes contains oxalic acid. Okay. Fine. Moving on. Next one. Sixth one. Any other acids? Natural acids.
So methanoic acid.
Methanoic acid. Okay. Fine. What is the common name of the acid? Okay. It's called methanoic acid. but we don't call it as methanoic acid in normal. We call it as something else. Okay, first, where do you find this methanoic acid?
Sir, ant sting.
Yeah, ant bites. Right, an ant bite, it pains because it contains methanoic acid, and you can obviously the exact name is methanoic acid only, but now common name what we use is formic acid. Is formic acid. Okay. Anything else, guys? Any other acid?
Sir, tartaric acid is also present in grapes, right?
Yeah, it is also present in grapes. Absolutely. Tartaric acid is in grapes also. Yeah. Okay. So these are all the different types of acids which are present in natural sources like this. Okay. I think this is it. I don't think there's anything else, or there are so many, but we don't have to go into the details. Okay, fine. So this is about your natural sources. What is the time? Do we have time? Yeah, 5 more minutes. Okay, cool. So that's about the first classification. Okay, so we saw organic acids. Say inorganic acid example can be HCl, HNO3, H2SO4. Right now, HCl is called. What is the name of the acid, guys? HCl.
Hydrochloric acid.
Hydrochloric acid. Okay, HNO3 is called as what? What is the name of what is the name of HNO3?
Some nitric acid.
Yes, nitric acid. Okay, H2SO4.
Sulfuric acid.
Yes, sulfuric acid. There is one more also you can know. There is something called as H3PO4. Can someone know the name of this? H3PO4?
Phosphoric acid.
Yes, phosphoric acid. Okay, I think these 4 should be sufficient. HCl, HNO3, H2SO4, and H3PO4. These 4 alone, you have to remember the formula as well as the names. Okay, because you'll be using them a lot in the reactions. And again, this acetic acid, okay, this acetic acid, what we have, anybody knows the formula? Acetic acid formula?
CH3COO minus.
CH3COOH. Okay, acetic acid. Okay, CH3COO minus is acetate ion. Okay, CH3COO minus is called, whenever you end with minus, obviously it has to end with E, right? So it is called acetate ion. Now, if you put a H, it becomes acetic acid. Okay, now there is one more thing also you can know, guys. Formic acid or methanoic acid. Now, one more thing I'll tell you, right? This acetic acid is also called as ethanoic acid. Okay, don't worry about so much about the things. But again, you can remember the acetic acid is also called as. Oh God. 1 second, guys. Yeah, CH3COH was right. I saw in the chat box. Yes. So yeah, so CH3 acetic acid is also called as ethanoic acid. Okay, and the formula is CH3COOH. Now, same way, you can remember this also. Formic acid is also called as methanoic acid. Anybody knows the formula here of the formic acid formula?
Sir, HCO2 or H2CO2?
Yeah. Okay, correct. It's HCOOH. This is how we write. Right. Now, please understand, people, you will be studying them in the, in your last chapter, that is carbon and its compounds chapter. Right. Remember, whenever the COOH comes, right, it's actually an organic acid. Okay. Now, what will you see is that in all of the things which we are, citric acid, tartaric acid, lactic acid, oxalic acid, all of them will contain the COOH common. Okay, you can see here also COOH is here there in ethanol, like acetic acid also. It is there in formic acid also. Say if at all you want to know what is the formula for oxalic acid, right? Oxalic acid formula, if you see, you don't have to remember oxalic acid, like, but the formula is like the COOH, like this. Okay, that's the formula for oxalic acid. So what you have to understand is by the moment you find the COOH coming, right, it's an organic acid. That's what you have to understand. Okay, now what and all acids you have to remember the name and the formula: HCl, hydrochloric acid, HNO3, nitric acid, H2SO4, sulfuric acid, H3PO4, phosphoric acid, and acetic acid, CH3COOH, and methanoic acid or formic acid, that is HCOOH. These formulas alone you have to remember, guys, and along with the names. Okay, now why? Because we'll be using them in the reactions. Like when you go for reactions, we tell now we didn't see such, but when you go for reactions, we'll be using all these things. Okay, right? What is the time? I think we'll stop with this for today. Right, we have finished only classification based on source. Now we have so many other classifications. Then we'll move on to chemical properties. Then we'll move on to base. Then we'll go to the salt. Okay. Any questions anybody has? Any questions, guys? Okay, fine. If there are no questions, I think we can stop here. Right. Thank you so much, people. We'll meet again next class, next week. Thank you so much. I'm ending the class.
Thank you, sir.
Thank you, sir.
Yeah,
Thank you, sir.
yeah.